Now in this next example, we already have a quadratic inequality in standard form. So what I'd like to do is solve the associated equation negative 6x squared minus 5x plus 4 is equal to 0. Now remember, we can always use the quadratic formula. It turns out this problem does factor, but if you don't see that very quickly, you can use the quadratic formula. So using the AC method to factor this, negative 6 and 4 multiplies to equal negative 24, and negative 8 and 3 are the factors that add to negative 5. So I can rewrite this expression as negative 6x squared minus 8x plus 3x plus 4, and then factor by grouping to get my two factors, 2x plus 1 and 3x plus 4. Since I'm setting those equal to 0, of course, each factor can be set to 0. The first factor gives me 1/2 as a solution, x equals 1/2. And the second factor gives us negative 4/3 as a solution. Of course, my next step, I want to plot those on a number line. These are called the critical values. I want to plot the critical values on a number line. So of course I'll place negative 4/3 on the left and positive 1/2 on the right. And of course now I want to check the regions to see what works. So I could choose as a test point for the middle region 0. If I plug that in, I get the inequality of 4 is less than 0. And of course that doesn't work. So this middle region isn't going to be part of my solution. And then really, in a sense, I can call it a day, because the outer two regions from the symmetry of a parabola would have to be solutions. We might want to sketch that parabola to sort of back up this claim. So another approach that actually wouldn't necessarily require us to do a test point first, another approach would be to recognize that the associated parabola y equals negative 6x squared minus 5x plus 4 is going to open downward because the a value is negative. So if I make just sort of a rough sketch of a parabola through those critical values, through those what are essentially x-intercepts for the parabola, if I make that quick sketch, I can see that to the left of negative 4/3, the parabola is negative, and then it's positive, and then it's negative again. And so the solutions, I want solutions that are less than 0. I want this expression to be negative. And that happens for values that are less than negative 4/3 or greater than 1/2. So my solution, my answer to this problem, of course, is negative infinity to negative 4/3, and then 1/2 to infinity. Example 3. We can solve in a similar way. Of course, I initially want to write this in standard form, subtracting 5. And then my next step is to solve the associated equation, x squared minus 4x minus 5 equals 0. This one we can solve by factoring. X minus 5, x plus 1 are the two factors that work. So x equals 5 and x equals negative 1 are my two critical points. So I want to plot the critical points, the critical values, on a number line graph, negative 1, positive 5. And then the quick way to get to my answer is to sketch the parabola associated with that inequality. So I'm sketching a graph of y equals x squared minus 4x minus 5. That parabola is going to open upward. So initially the values are positive, then they're negative, and then they're positive again. And I'm interested in the solutions that are negative because I have that less than or equal to 0. So negative or equal to 0. And so I'm going to include the boundary points this time. And my solution is negative 1, 5. So that third step, checking the regions, I did that purely graphically this time. If you're unsure, if you want to double check, we could use a test point x equals 0 is often a good choice. If I plug that into the original inequality, I get 0 is less than or equal to 5, which, of course, makes sense. So I feel pretty good about this as my final answer to the inequality. And now let's look at one more, example 4. Of course, this inequality is already in standard form, so I want to solve the equation x squared plus 12x plus 36 equals 0. And what you might notice, it's really nice if you do, this is a perfect square trinomial. So this is going to factor as x plus 6 squared, which of course means there's only one critical value. The only thing that gives us a solution to that equation is -6. So I can plot that critical value, sketching a number line, plotting the number -6. But now, because there's only one critical value, we have to be careful sort of how we think about this. If I use test points, I want to make sure to use 2 test points. So -10 and 0 would be good choices. I really could choose any number. -5 and -7 would be good options as well. If I plug 0, I get 36 is greater than or equal to 0. If I plug in 10, I get 100 minus 120 plus 36, which is a little harder to work out here, but I get a positive 16 from that. So both of these satisfy the inequality, so both of those regions work. So I just did my third step, checking the regions with test points. From this statement, though, it's pretty clear this is always going to be greater than or equal to 0. And so if you look at that factored form, x squared plus 6 squared is greater than or equal to 0. That's essentially what this initial inequality becomes if you factor it. That's always going to work. 0 is included because it's not a strict inequality. The associated parabola, y equals x squared plus 12x plus 36, opens upward with just that single x-intercept at that point. And so the final answer to this problem, of course, is all real numbers, -infinity to infinity. So using test points can help. It can help give us some concrete basis for our answer. But thinking about the expression and what comes out of a factored expression, or thinking about the graph of the parabola and seeing when it's positive and when it's negative, thinking of the number line graph as something that represents the x-axis, all of those methods are great ways to think about how to check the regions once you have the critical values. So it's kind of a two-step process. You want to solve the related equation to find critical values, and then check the regions on the number line created by those critical values. So in this sense, because there's only a single critical value, the middle region got squished and combined into just a single point. And we get this wonderful solution of all real numbers. I hope you enjoyed the video. Thanks for watching.